Hello. Well, it looks like it's time. Welcome back, everyone. And happy midterms week. We're at the halfway mark officially now. Midterms won't be anything fancy for this class. Pretty much what I'm going to be doing is on Friday, I'll pull the grades from WebAssign on the assignments that are past the due date. I'll grade all the quizzes. Looks like it'll be up to quiz 5 since we pushed this one down by a week. And then I'll just put what your grade is here as a percentage, convert it into a letter grade as your midterm grade. So just really, literally, it's going to be what your score is midway through. The bigger announcement is our second exam will be a week away from today. So the first document to pay attention to is going to be the formula sheet. I'll have this printed on the very last page of the real exam. And it's a good idea to orient yourself with what information is here to kind of tell you what you have to have memorized and what information is provided. And just like we did on the other exam one, there'll be a version 1 of exercises and a second version down below as well. Well, any questions at the moment, folks, about the exam or otherwise? Okay, well, because we don't have time for a review built into our schedule, just like exam 1, I'm going to keep the actual exam pretty similar to what we were doing in class, as well as what you were doing in both WebAssign and on the quizzes. We're going into section 3.6, just so we don't get too far behind on the schedule. But the exam is going to end in section 3.5. That one was on the chain rule. 3.4 was on product rule, quotient rule. And 3.3 was on the first set of differentiation formulas. As far as sections 3.1, 3.2 goes, I'm not going to ask a whole lot of questions from those. There's going to be a tangent line equation, and you can use differentiation formulas to solve it. And there'll be a problem where a graph is given of a function, and you have to sketch the graph of its derivative. Well, that's going to be our second exam. For what we're doing now, we're going into section 3.6. We started it getting through example 1. And if we have time, we'll begin section 3.7 on differentiating logarithmic functions. Well, any questions at all then, folks, before we start out back in 3.6? Okay, well, let's take a look where we left off. It's always kind of takes a bit of time to refresh after a long weekend. Well, question first, Naomi says, so nothing we do today will be on the exam. Yeah, that's right. Our exam is going to end, or our exam 2 content is going to end in section 3.5. So really 3.6, what we're doing today, is going to be the first set of problems that you're going to see on exam 3. But you know, we still might differentiate something in 3.6, 3.7. So whenever we do any problem that looks like it's exam 2 related, I'll be sure to call that out just so we'll get some perspective on the problems on those sections. Other questions at the moment? Okay, well, let's jump back into 3.6. We were looking into that differential equation right there. We're saying the rate of change of y, whether it's a population or amount of mass or amount of money, any quantity, if it changes with respect to time, if the change of it with respect to time rather is proportional to its size y of t, we get this equation here. The very first thing we want to talk about is this differential equation has an automatic solution. In a pre-calculus course on algebra, we pretty much study that equation right there by where the red dot is. But now we're looking at both pieces, the original differential equation and its solution down below at the same exact time. Theorem 2 essentially becomes a formula, so when the calculus portion comes up in our upcoming problems, we'll be sure to make a big deal out of it and how the formula works. And they're tricky because the example 1 that we've done really only has to be done one single time. The idea was, if you have this function right here, oh, hang on, I have a issue with my word layout. I don't see the drawing tools. Let me get this Word document working correctly. Probably just needs to be restarted. I don't know what I would do without the digital pen. I've become pretty reliant on it. Okay, now it popped back. That's weird how that happens sometimes. Okay, so what I was trying to circle was this equation right here is essentially the same as this one that we see down in theorem 2. We just plugged in the initial value and the relative growth rate to make it more concrete. So we said K was the growth rate, Y at 0 is the initial population size. The major thing we want to connect is this differential equation right here with the provide solution. So this is a problem that really you only have to do once. If you have something of this format with any other initial value and any other growth rate or decay rate, when you go to differentiate dp dt, you'll absolutely get k times p. Now we did this from scratch. This was a chain rule problem, a pretty tricky one. We differentiated this function as we saw it here. The constant multiple rule left the 750 unadulterated, just still multiplying. Then we analyzed the inner function versus the outer function. I guess that's highlighted just to show the growth rate. When we differentiated that, we chained on this derivative. But the major thing we noticed is this whole piece right here is the p portion. Then the chain rule derivative, this part, when we got that, we got the relative growth rate k come out again. So we got down to k times p at t. So this is a really nice connection, and it makes it so that as far as the calculus goes, if you use this formula, you don't have to work super hard every single time and reinvent these steps for each new growth model or decay model. So the punchline to this problem, once again, is that this derivative highlighted in yellow is powerful. It's the automatic derivative to every function of that form. And for the next 3 exercises, we're going to just see how that works in action. Any last questions, folks, on the refresher on example 1 before we try out the new problem? Okay, well, here's how our new context goes. We're told a bacteria culture, this could be yeast cells, it could be, say, E. coli bacteria, something along those lines. But some bacteria culture, we're told, grows at a constant relative growth rate. Well, that tells us a lot of information already right there. From that statement, we can say that the derivative of p with respect to time is k times p. P is going to be our population size at time t.
Did you hear me go, God damn it?
Oh, sorry, that sounds like an open mic. So we get this statement right here, just from the statement, grows at a constant relative growth rate. But then theorem 2 above tells us we have an automatic solution to this. The solution is p at t, that's going to be the size of the population at time t, is equal to, I want to match up the color coding, so let me peek. P of 0 will be in green. So p at 0 times the base e exponential to the power of k times t. So that one statement right there gave us the differential equation, and we have this automatic solution that comes right out. Reading through the context, we're further told the bacteria count was 600 initially. And that initially right there is a major, major keyword. 600 initially is now telling us that the population size at time 0 is 600 bacteria. I'll say 600 cells for short. So we have this initial size in the Petri dish, 600 cells, and we're further told 7,500 after 3 hours. That's even more information, so let's take this. That's telling us that the population size at 3 hours, so P at 3, is 75,000 cells exactly. So there's a lot of context to break down. We have the initial value here, a secondary value here, sometimes also called an initial value, the differential equation, but we're going to focus on the solution, P at t equals a P naught e to the kt. Part A, finally, getting to that portion, says, find an expression for the number of bacteria after t hours. And this is that expression, but what the instructions are really saying for us to do is find the value P at 0. We've already indicated 600, but then also find the relative growth rate K as well. Well, we're about to solve for both values. Well, K is the bigger value to solve at the moment. Any questions to this stage of the analysis? Okay, let's take the next step and just plug in the initial size. That's supposed to be the number 0. It's starting to look like the number 6 to me. Let me fix that. Population size at time t is 600. I'll write it without the unit, just as a mathematical expression, e to the power kt. So our next step is solve for k. That seems kind of mysterious in a certain sense because it may not look like there's enough information to say what the relative growth rate is, except if you have that other equation, we can bring that into the problem and actually use it to solve for k. So let's restate that equation. The size of the population at time 3 hours is 75,000 cells. Okay, so here it is, just restated. Well, one thing you can think about when you write this down is we have an equation for population size at any time. So you could also write population size at time 3 hours is 600 e to the power k times t. So on one hand, population size at 3 hours is 75,000 cells. On the other hand, it's equal to this. We can just equate both of those values. Or another way to visualize this, in place of the left-hand side P at 3, we're just plugging in the output, 75,000. So 75,000 equals 600 e to the power kt. That's now an equation from which we can solve for the unknown k. Or hang on, looks like I did make a mistake when I wrote this out. When I plugged in the value 3, let me highlight that mistake. It's kind of a silly one. When I plugged in a value 3, I was replacing this t variable here with 3, and I have to replace that t variable at the same time. So for a 3 here, that means a 3 would go here as well. Sorry for the distraction with that misstep there. I'll write this in as k times 3, and now that's an equation from which we can solve for the one unknown, just k. Well, if we're going to solve for this, first thing we want to do is isolate the exponential function. So let's take 75,000, divide by 600. We get exactly 125. So 125 equals e to the power of 3 times k. Once we get here, the next step is we're going to use properties of logarithms. Again, just another call out to those notes. Down below are a couple worksheets or review material and then a worksheet on properties of logarithms. And I'll cite those properties as we use them, much like how we were reviewing the exponent laws back in the day in prior sections. The property we need to use here is that natural log of e to the power, let's just say, maybe not p, e to a power r is always equal to just r. The idea is That's an exponential function, and it has an inverse that passes the horizontal line test. The functional inverse is the natural logarithm. So when you do a composition like this, the natural logarithm of a base exponential, there's a true cancellation going this way. Those cancel out and you just get the exponent r. So what this tells us is, on this line, if we take the natural logarithm of both sides, here's what it would look like. Natural log 125 equals natural log e to the power 3 times k. But by taking this step, we've effected a cancellation on the right-hand side. All that's left is the exponent 3k. Much like on the formula we cited on the right, the exponent r is playing the role of 3 times k. So natural log of 125 equals 3 times k. A lot of algebra just to get to this step, but we're finally here. We divide both sides by 3, we get natural log of 125 divided by 3 equals k. Then finally, we can take this entire thing, plug that in for the power k right as we see it here. And the conclusion to the whole problem, part A, find the expression of the number of bacteria after t hours, is that population size at time t is 600 e to the power. Just to make it read a little bit better, I'm going to put the variable t first. T times, then k, for this part, natural log 125 thirds. And that whole thing finally is our population size at time t. Well, now that we have that, we can do a function evaluation, do a little bit of calculus with it next. We'll also do another scenario where we're going to solve an equation. It goes about like this as well. But any questions or comments, folks, getting to these exponential growth model? Haley says, I remember doing this in pre-calculus. I find the formula k equals natural log p of t divided by t works, so you don't have to make a mistake when moving numbers around. That's an awesome formula. Let me cite this here. Works well with solving for t as well. Just switch k and t. So the formula is k equals, let me know if I miscopy this, natural log p of t divided by p divide by t. And I think that makes sense because, yeah, if we say divide by 600 here, that looks like the divide by p part. Take the natural log of both sides of this, that's the natural log part. Then we would be dividing out this part, the k. Yeah, it looks like it's kind of just solving this for k, or going to this formula right here, solving it for k. You get that formula there. That's awesome. Thanks for mentioning that. That's a great shorthand, getting to this step down below. Other questions or comments at the moment? Okay, so there's the algebraic way. It takes a little bit of time to get through. But if you just solve this where the red dot is, 4k in the very first place, you get this awesome formula right here. So that's a great approach to take as well. I'll leave it up to the class how you would like to do it. And if you decide to cite the formula, use it, say even on exam 3, you can never lose points for knowing stuff. I think that'd be a great approach. Well, next thing we'll do is evaluate this. Notice the difference between these two questions, though, in parts B and part C. Part B is saying find the number of cells in 2 hours, but part C is saying find the growth rate, they mean of the entire population of bacteria, at 2 hours. They're very different questions. One's a function evaluation in part B. The other one is a derivative, dp dt, where we're going to use this formula again that we cited up the top. So let's get through part B to start. That's kind of a relaxing problem, just a function evaluation. Population size in 2 hours just means swap the variable t for the value of 2 hours. We'll get 600 e to the power 2 in for t times the natural logarithm of 125 divided by 3. And here's where it gets a little bit tricky. If you have a calculator handy, let me know if you're getting any different kind of values. This one, I'm never going to be very picky when you do this on exam 3. If you give me a number that's in the right ballpark, then I'm not too worried about rounding in the middle and that kind of stuff. Now, if you put this on paper before you even put it in the calculator, that's where all the partial credit is based on. So if there's a major mistake and your number is way off, I would give essentially all the credit for this right here, shown on paper. But where it gets a little bit tedious and a little tricky is WebAssign is expecting a very, very accurate answer. They don't want us to round in any middle computations. That's why we didn't do approximation here at all. We are going for the exact answer, and getting the exact answer to the nearest cell can be tricky. So let me know if you're getting anything slightly different, and I can explore how to do this in various calculators. In this calculator, mainly just good for a classroom demonstration, it would look like this. 600 e to the power 2 times natural log 125 divide by 3. So I'm getting exactly 15,000 cells. And if I did any approximation in the middle, I'm going to possibly be quite a bit off. Let me put this down on paper, 15,000 cells. So the fact that we're dealing with an exponential function is what's making this tricky. Imagine you did take this k right here, it's natural log 125, divide by 3, and you use that as an intermediate value, an approximation in the middle of the computation. Here's how this might change then. You would take this 2 times the value for k, and let's say you rounded to 1 decimal point. It would be a 1.6, and that's actually quite a bit off. Sure, we're just talking about cells, but this is a model that could work for money under the context of continuous compounding, although that's kind of rare. I don't see a lot of banks with continuous compounding. If this was money, we're short hundreds of dollars and people are going to be really upset. For more accurate, and put in the 09, we're still off. I'd probably give full credit if I saw that number in exam setting. Like I mentioned before, even if I saw this, it would tell me you approximated a lot, but you understand the concept. But WebAssign will throw a fit at that, unfortunately. They're expecting a highly accurate answer. So if you go 09, that's still probably going to mark the question incorrect. We have to go really far if we want to get a highly accurate answer. 437, 912. Notice when I'm at the 437 rather, we're about there. For rounding to the nearest cell, this would round up to 15,000. So the short story for this is, in WebAssign, they want it exactly like this when we say the growth model. And when we're doing an evaluation, if you approximate this, put in a lot of digits to get the accurate answer. I would say 8 digits is a good idea for this kind of problems. We used 1, 2, 3, 4, 5, 6 digits past the decimal point to get to rounding correctly. Well, any questions at all, folks, on getting that in the calculator, obtaining that value? Okay, now we're going to do the calculus part, but this problem is kind of interesting because I did have an interesting question one time when I ran this class where someone asked, who's counting these? That would take forever, right? To count 15,000 cells. So if you're curious, the way this really works is the bacteria is put on a petri dish, which is just some kind of substance, a jelly that has some kind of nutrients that the bacteria culture is going to grow on, some kind of agar, I think they usually call it. Then they put this petri dish under some kind of system that throws up a photon of light, many photons of light on a fine, fine grid. And if a photon is intercepted, the assumption is a bacteria cell hit it. And so that's a count. There'll be light going up that counts on an above sensor, the light that came through. It does a difference, and it gives you a pretty accurate approximation of how many cells there were based off how much light was intercepted. So that's the kind of the rough story on how these are actually counted. No one's being abused doing this by hand. So we got 15,000 cells at 2 hours, but this is growing exponentially. So the question is, how fast is the population changing or growing at the 2 hours? Here, you could work from scratch, differentiate this model right here, plug in 2 hours, but we don't have to. We know the derivative. That's actually the first piece of information we had, even before the growth model we have right here. So to solve this kind of problem, this is the calculus of the section. All we need to say is the rate of change of the population size with respect to time t, evaluated at a certain time, 2 hours, is going to be the relative growth rate, k, times the population size at 2 hours. And we just so happen to know that population size. We also know the relative growth rate, k. So this one is, although it's a calculus question, we already knew the derivative. We're just going to do another evaluation. Take natural log 125 thirds, multiply it by the 15,000 cells. The unit on this is going to be formed from the unit in the numerator, cells, per the unit in the denominator, hour. So much like, say, miles per hour or some other quantity in calculus, this is now a rate. So this is like a speedometer of how fast the population is changing at the 2 hour mark. And eventually this model is going to fail. It can't grow exponentially forever. Eventually it's going to run out of space, run out of nutrients. But if the model is accurate at the 2 hour mark, the derivative will be as well. So it's another calculator operation, but any questions on just putting it down on paper here? Okay, so here's what we'll get. Natural log 125 thirds times 15,000. So altogether, it's 24,141.6 cells per hour. So that means if we check in another hour, because it's growing at this rate, it should be about this plus a 24,000. That's a rough approximation, but it's close to the ballpark. The trick is, or the problem with that is, if we do the same problem at 2.5 hours, we'd have to multiply by the population size at 2.5 hours. The growth rate is going to be even bigger at that point. So even though this is right in cells per hour, we can't necessarily add 24,161 to this value to get an accurate count, because this is just the instantaneous rate of change, specifically at 2 hours. And every additional unit of time, every second that goes by, the growth rate is increasing as well. So it's kind of an interesting problem with calculus, and just a way to tie together the concept with the derivative. Let's put in just one additional statement. Haley says you don't have to round to the nearest cell, since you technically can't have 0.6 of a cell. Well, in this problem, because it's a growth rate and it's just an approximation of how fast it's going, it would be okay to say approximate to the 0.6 or even more decimal points. Much like, say, this one is exactly 15,000 cells. And if we put in the population size, or the entire model, P of t equals 600, e power t times natural log 125 thirds. Here's our model altogether. The units on this look kind of crazy, but we want to change from a y-axis going from, say, 0 to maybe 50,000 to really see the scale on this truly. So essentially what it's saying is, right at this 1 hour mark, if I can hit it just right, there we are, right at the 1 hour mark where there's 3,000 bacteria in this population. We know that there's not going to be exactly an included amount of 24,141.6 cells. What we're saying is it's just going to be the rate at which the population is increasing by. So even in this context where we can't have, say, a decimal amount, we could have this just for a growth rate specifically. And another way to think about it is maybe you could imagine that, what is the word, meiosis or mitosis? I think it's meiosis, or maybe mitosis, the division of cells. I'm pretty bad at biology at this point. It's been a while. Mitosis, thank you for that. We can think in terms of mitosis. A cell is about to divide 60% of the way through. But other questions so far? Okay. Well, these problems are kind of interesting as an applied problem in this section. That's the end of the calculus, just getting the derivative evaluated at a specific time. Part D is another question much like part B, except the unknown this time is the variable t for time. And like Haley mentioned, you can do this a couple ways. You can work this variable here if you like. Just swap the k value and the t value in this expression to try out that formula. I'll do it from scratch since that's the way I'm most used to trying to do it. So for a different approach without using the formula, here's how we can find when the population will reach 200,000. One thought is, if you have a graph out like this, you scroll way, way out until you see 200,000, put in another y equals 200,000. The intersection of this line and the dot in blue should be about the right time. But doing this kind of problem, say in an exam setting, we don't have Desmos. So let's do it from scratch algebraically or citing the formula. This is a great check though. You can put in just the value in question, put in the original function that you derived, and that's the solution where those curves would intersect, the very first coordinate. So I'm expecting 3.6 hours. Let's solve this algebraically and see exactly what it'll come out as. We need to use this model right here up on top. And we're trying to solve when will the population size at time t reach 200,000. First thing you can do here is take this entire right-hand side, substitute it in for population size at time t. You would get 600 e to the power t, natural log 125 divided by 3. That's the entire right-hand side, replacing p of t equals 200,000. Then this is essentially just like solving for the growth rate k, but this time we're solving for time t. Divide both sides by 600. That gets us started. So 200,000 divided by 600 comes out to a repeating decimal, or as a fraction if you prefer, 1,000 thirds. So e to the power t, natural log 125 thirds, is 1,000 divided by 3. Only step I took here was divide by 600. Now we need to cancel off the base e exponential, but that's done just by taking natural logarithm of both sides. On the left-hand side, there's our cancellation. Now we've freed out the exponent, t times natural log 125, and there's a bit of an error, the way I wrote this down. When I wrote natural log 125 thirds like that, that's not quite right. That's going to give us a different number. Natural log 125, close the parenthesis, and then divide by 3 is not the same as what I put down on paper there. So watch out for those kind of silly mistakes that can definitely affect the answers as, say, an exam question or a problem in WebAssign. Just for emphasis, natural log 125 thirds is that as a growth rate. The natural log 125 thirds, like that, quite a bit different. We get that value out instead. So let me backtrack here, fix that division. Natural log 125 divided by 3 like that. Make sure you close the parenthesis right there. Again, that's a really, really common calculator error that can be frustrating, so watch out for that one. So it's t times natural log 125 divided by 3 equals natural log 1000 divided by 3. We'll multiply by the reciprocal of that natural log 125 thirds, and t comes out as 3 divided by natural log 125 times natural log 1000 thirds. That formula that Haley cited is starting to look kind of nice because that is a lot of steps. I'm going to practice with that and see how it goes, just so for my own education on doing it in a different kind of way. But if you get through the steps, the last thing to do is put this all in the calculator. 3 over natural log 125 multiplied by natural log 1000 thirds. If you recall the graph, that's the same exact value. Rounded to two decimal places, we'll say 3.61 hours. So time will be 3.61 hours for the population size of this bacteria to reach 200,000. The growth rate at that point is going to be pretty gigantic. It'll be 200,000 times the relative growth rate right here. Well, any questions at all, folks? Getting through part D. Okay, well, we did it. This is essentially how these problems kind of go. A lot of it's review, so that's kind of nice in a way, just looking at exponential growth, exponential decay. When the calculus crops up, it kind of sneaks in. So the keyword to watch out for is growth rate or decay rate. The major keyword being rate itself is indicating you're dealing with a derivative now, not a function evaluation. And just for the sake of really hammering down this derivative, changing at any time, at 2 hours, we're growing at a rate of 24,141.6 cells per hour. But what about at 3.61 hours? That's an approximate value. Population size is exactly 200,000. Multiply by the relative growth rate again, natural log 125 divided by 3. So it's telling us at the 3.61 hour mark, the population size is growing at a rate of 321,887.6 cells per hour. Completely and massively different, but that's just because it's growing exponentially. At every additional hour, this rate is changing. At every moment in time that goes by, this rate is just getting larger and larger by a lot. Well, we're going to turn this over from exponential growth now into exponential decay. And exponential decay is not too bad after we got through the growth model. One reason being is usually in a discussion about exponential decay, you have extra tools. The half-life comes up often, and that's a wonderful formula for half-life because it immediately gives you the value of k in a really fast-to-use formula. So it tells us if a quantity is decaying exponentially, that means just from this statement already, we're looking into a model. I'm going to use m to refer to the mass of a quantity at time t. The rate of change of mass at time t is k times m. That's a differential equation, and I didn't think through the mass space I needed. The solution is going to be the amount of mass at time t will be the initial mass, m at 0, times e to the power k times t. So decaying exponentially gives us all this information. And one bit more. We have that the relative decay rate, k, is now negative in this problem. So if we get a positive quantity, we've made some kind of weird mistake, algebraically probably somewhere. The half-life is just going to tell us the amount that's going to remain. Excuse me, it's going to be the amount that remains. Getting kind of mixed up on that. The half-life is easy to think about, sorry. The half-life is going to tell us how much time must go by for only half of the initial amount to be remaining. Sorry, for some reason that was hard for me to say in words. It's got a nice formula. It goes like this. Lambda equals negative natural log 2 divided by k. And that formula can really be written in two different ways. This is nice if you're solving for lambda, like we'll do in, say, example number 4. But if you want to solve for k first, like we'll do in example 3, it's not in its most convenient form, but just flip it around. You could take a multiply both sides by k, divide both sides by lambda, and k is now equal to negative natural log 2 divide by the half-life lambda. So we have two dual formulas. The textbook states this one, but this is a great one to have just at the ready to save one algebraic step. All of the steps you can save are helpful. And just because it took me a moment to think about this or say it in words, what we mean specifically by half-life is if we have this as the model, then the amount of mass at time lambda is going to be 1/2 of the initial amount, exactly 1/2 of m naught, or m at 0 rather. So that's our formula altogether. And it's in a kind of funny form. There's a natural log 2 that is involved there with a negative sign. I think it's kind of a weird way to write it because if you're thinking in terms of properties of exponents, we have this one. Natural log of some, say, base b to a power I'll write in as r is just the same as r times the natural logarithm of b. We'll be looking into that exponential property quite a bit in the next section. Essentially, what happens is r can transfer down and become an exponent in the world of logarithms. So if you look at that negative natural log 2, you could express that as a -1 times natural log 2. Then this is a true exponent. You can go forward or backwards in this formula. You can take this, make it an exponent on 2. That's now natural log of 2 to the power -1. So what this is now telling us is that negative natural log 2 is really natural log of 2 to the power of -1 is just 1 over 2 to the power +1, or just 1/2. So this formula would have made more sense. Natural log of 1/2 just kind of sounds like you're talking about half-life. But for reasons unknown, maybe people just didn't like fractions when they stated this, they did all this work right here and put a negative in front instead of using the 1/2 for half-life. But either way you say it, the formula is going to work exactly the same way and give you either the half-life lambda or the relative decay rate k. And notice it absolutely is negative. We have a negative value here, and all other quantities are positive. Well, that's the formula discussion. Any questions about the underlying formula at the moment? Okay, here's a scenario that's kind of interesting. The half-life of plutonium-239. This is the bad stuff that you can turn into a bomb, eventually turn into a missile, ICBM, that kind of stuff. So these are the kinds of things that people want to be really mindful of and try to control globally. The half-life of this one element is approximately 24,110 years. So it's actually pretty stable. That's unfortunate. It's a nasty element that can cause a whole bunch of bad things to happen globally, which is stable. It's not going to go away in our lifetimes if we have a decent amount of it. So the scenario of this problem says a shipment of 1,000 grams of plutonium, we're referring to 239, arrives at a secure location where it's to be stored indefinitely. There's plenty of sites like that across the USA. We want to find an expression for the amount of mass of plutonium-239 remaining at time t. Well, the moment it said half-life, it tells us we're talking about a relative decay model. So this differential equation is on the paper, and so is this model for the mass. So That one keyword there coming up means mass at time t is an initial mass, m at 0, times e to the power relative decay rate k times t. First thing we'll solve for is m at 0. Has anyone spotted in the context what that value should be? Yeah, absolutely, Naomi. It's the initial 1,000. So when it says a shipment arrives at a secure location, we're going to say the moment it's checked in, the clock starts. That's mass at time 0. And they're probably going to weigh it to make sure no one stole any and make sure it's really 1,000 grams. But it's a pretty stable amount. So if it left one location at this amount, it's probably going to arrive at the next location very, very close to that same amount. So mass at time 0, 1,000 grams. I don't know if that's a lot or little, so I try not to Google problems relative to this chemical too often, but we're just going to go with 1,000 grams or 1 kilogram if you prefer. So we can plug in that value directly here, mass at time t equals 1,000 e to the power k times t. Part A is just like part A on example 2. We're trying to solve for the initial amount relative to k rate k, but this one's a lot nicer. Much like if you use the formula that Haley Starks stated in example 2, you could have solved for k pretty quick. Same idea here, and it's a nicer formula to work through. We know the half-life value when they said the half-life is this approximate amount, 24,110 years. So let's start by writing down lambda equals 24,110. Once we know that lambda value, our work is essentially done. We know the value for k as well. This tells us k equals negative natural log 2 divided by half-life at 24,110. So we're done with that. We can just plug it right back into k. We're on our way with this problem. So the mass of plutonium at time t, where t is number of hours after it arrived at the secure location, is 1,000 grams, the starting amount, e to the power of, I'll put time first, and let me organize that a little bit better. There's also a negative sign, so I'm going to go time, negative here, natural log 2, divide by 24,110. So the part in blue is k, but putting the negative in front so we don't accidentally say t minus something, it has to be multiplied. You could put extra parentheses in there, but I think it just reads better, especially in the calculator, if you put it in like that. So we're going to look into a couple more questions. One is going to be an evaluation problem. The other one's going to be a calculus problem. But really, it's kind of a redo of example 2 just now for a decay problem. If we want to know how much of the sample remains after 100,000 years, we could give a pretty good approximation to that, thinking about what half-life is. One half-life gives you half of it. Another half-life gives you half of this, so 1/4, and so on. And even though the half-life isn't 25,000 years, if we approximated it really, really roughly as 25,000 years, that means 4 half-lives have gone by. So that would mean take the 1,000 grams altogether, times 1 half-life. That would be, say, we're giving a really, say, rough estimate to see what it'll come out as. We say half-life is 25,000 years, then 1 half-life's gone by. In 50,000 years, 2 half-lives have gone by, so we raise that to power 2. 75,000 years, 3 half-lives. And now finally, at 100,000 years, not exactly 4 half-lives, but pretty close if we're rounding bluntly, we're expecting something on the order of magnitude around 62.5 grams. our value is going to probably be a little bit less because a half-life is a little bit quicker than 25,000 years. So this gives us some kind of back of the envelope computation. If we come up with, say, 600 grams, we're way, way off. If I come up with 3 grams, I'm way off again. So let's keep that in mind. We should be around that figure. How will we do it? In fact, we're just plugging 100,000 in for the variable t. So mass and 100,000 years. We are all long gone by then. We'll hope that human society still exists. It's 1,000 e to the power of negative 100,000 years again, times the natural log of 2 divided by 24,110. And even though this problem is going to be on exam 3, once again, I just want to shout out to putting this on paper is essentially all of your insurance against making a small mistake in a calculator, which is easy to do when you have this much stuff you're putting down. So show that on paper and you're going to get essentially all the credit. If your number is off, and this is a 5-point problem right here, I might take off just a half a point, something like that. Again, if you have a calculator out and if you're getting something different, don't hesitate to ask. I'm happy to look into this computation closely to see how close we are. Just want to put that back just for the reference on our estimation. Now let's plug in 1,000 e to the power of negative 100,000. And let me just make sure I've got the zeros lined up. That looks about right. Natural log 2 divide by 24,110. To the nearest tenth of a gram, that'd be 56.4 grams altogether. And yeah, it's in the right ballpark of this answer here. It's in the right order of magnitude. We got pretty close, rounding up the half-life to 25,000 years. So in actuality, in 100,000 years, 56.4 grams is what's going to be left at this secure location. Who knows what's going to happen to that secure location? 100,000 years is a long time. Anything could happen. Maybe geologically, there could have been a volcano that emerged and wiped it out. But if it stayed secure, this is how much is left. Any questions at all, folks, on the evaluation part right there before the calculus part? Okay, and we highlighted this before we went on to the weekend on last Thursday. The key word here is rate once again. The moment it's asking for what rate it's decaying, we have this differential equation ready to go. But notice another thing that's kind of interesting. When it says decaying, this automatically implies the derivative or the rate, let's say it as a derivative. The derivative must be negative. If we're talking about populations or amount of mass, a positive derivative means something is increasing, but a negative derivative means something is decreasing in population or in mass. If we're talking about velocities, a positive derivative means something is going up or maybe to the right, whereas a negative derivative would mean something is going down, thinking about gravity, or maybe to the left, depending on the frame of reference in the problem. So now working this out, we're going to say the rate of change of mass with respect to time. This is the total derivative at any time, but we're evaluating it at 100,000 years. So we put a little bar, say evaluate at time equals 100,000. You could put on the units just to emphasize the quantity you're calculating. This is going to be relative to k rate k times the mass, m at 100,000. We have the values for those. Relative to k rate is right here. And you notice it's definitely coming out negative because there's a negative sign. Negative natural log 2 divided by 24,110 is going to multiply we'll use approximated value, and WebAssign operates in this way as well. They ask you to round an answer, and the answer comes up in the next problem. They're going to actually grade on two different things. They'll look into if you use the approximate answer, which they're expecting. They'll also be checking another answer. If you did the exact value right here, they'll accept that as well. So usually for these kind of problems, it's assuming you're going to use the approximation on the next step. I'll go along those lines. 56.4. The unit is no longer grams. This is going to be grams per the variable in the denominator, year. So this is how much the plutonium-239 is disintegrating per year when 100,000 years have gone by since it was dropped off at that secure location. So let's see what that number comes out as. Notice we're rounding this one to 4 decimal places, so it sounds like a small quantity. Negative natural log 2 divided by 24,110 times 56.4 grams gives us this quantity, negative 0.0016. Grams per year. So if someone is around at that time, this is how much it's disintegrating per year at that 100,000 year mark. Not by much. There's still a lot left, 56.4 grams, and every year, only that much goes by. Really, still the half-life is relevant. Every additional 24,000 years, this just gets divided by 2. So that's the end of the calculus question. Any questions or comments at all, folks? Getting down to that answer there. Okay, well, this is another interesting kind of calculator question. We want to know, well, if there's 56.4 grams in 100,000 years, how long will it take us to go from 1,000 grams to just 1? That's another equation solved kind of problem. And here's how the algebra would look like on this one. Here's what the algebra would look like on this one, rather. Let me bring that back where it was. We're going to need the original model to start out. So here it is. And from this piece of information here, we can just say mass at time t set equal to 1 gram, or G for grams. Then on the left-hand side, just like we did on example 2, we input the model. So this whole thing, just trying to scroll to the right amount here. So on the left, I'll put in 1,000 e to the power of negative t natural log 2 divided by 24,110 set equals to that 1 gram. So I'll drop the unit here until we get to the solution in time for t. But just like before, all we are doing is substituting in place of the function notation mass at time t, the expression for that mass. So once we go down here, our goal is just to solve for the variable t altogether. That's not too bad. It's the same kind of steps. There's a lot of steps. So once again, shout out to Haley's formula on example 2. That could be applied in this problem right here to solve for time. But going this route, let's divide by 1,000. You'll get e to the power negative t natural log 2 divided by 24,110 equals 1 divided by 1,000, or 0.001 for 1,000. Next step, take the natural logarithm of both sides. So natural log e to the power negative t, natural log 2, 24,110 is now the natural log of 0.001. Very large negative number on the right-hand side, but we have an extra negative sign that's going to flip it back to positive. Next thing, though, is we get that automatic cancellation with the function against its inverse function. So the left-hand side is now just negative t times natural log 2 over 24,110. And we're kind of on our way. All we're going to do is multiply by the reciprocal, also multiply both sides by the negative sign. So t is now negative 24,110 over natural log 2, multiplying natural log 0.001. So recall we scrolled for just a moment and peak, 100,000 years to get to 56.4 grams. So we're expecting quite a lot of time going by on this. If we got an answer, say, 150,000 years, that probably wouldn't seem about right. So for the calculator step, it's negative 24,110 over natural log 2 times natural log 0.001, and that's the amount of years. We're rounding it to the nearest tenth of a year. So in terms of the nearest tenth, 240,275.1 years. In other words, plutonium-239 is sticking around for quite a while. I don't know if 1 gram is dangerous at that point compared to the 1,000 grams. I'm not too sure about the size of those as far as it relates to making nuclear bombs. But that's an impressive amount of time for that material to finally go away. Any last questions at all, folks? Getting to that last time value there. Okay, well, we're nearly done with this section. Again, it's meant to be just kind of a short applied section, talking about models we're familiar with, but bringing calculus back on the paper, like on the last problem that we went through, or last part rather. There's one more problem we're going to get through, which its major purpose is just to think about half-life a little bit more, become slightly more familiar working with that formula. It's also kind of tricky because it doesn't tell us a lot. We're looking into a sample of tritium-3. If I recall right, last time I looked into this is something that's used in medical imaging. I think it's a contrast of some kind before you do some kind of CT scan, potentially. I would have to Google that again to be absolutely sure. We're told that it's decayed to 94.5% of its original amount after 1 year. So as contrast to the plutonium-239, this one's more unstable by quite a lot. It's disintegrating rapidly before our eyes in just 1 year. But notice what's kind of missing here. They never told us the initial amount whatsoever. We're just told there is some original amount, and we're told the amount it decayed by. So this part is unknown. We can still call it mass at time 0. That's the best we can do with it. It's an unknown quantity. It also tells us that a sample of some original initial mass decayed to 94.5% after a year. We can re-express that by saying mass at time just 1 year, or the 1 year inside there, is, convert this to a decimal. From the percentage, we'll go 0.945 of its original amount, means multiplied by the original or initial mass, m at 0. So it's a really short context, but it's informationally dense. It's giving us a percent it's decayed to after 1 year. And the question is, what is the actual half-life itself? That's the unknown this time. Once we get the half-life, we'll also know the relative decay rate K. We can answer the follow-up question down below pretty rapidly. So this one looks like it's just purely an algebra question this time. But again, its purpose is just to think about half-life a little bit more. And the key concept about half-life is your half-life value is completely independent on whatever your initial amount is. This could be any value that's non-negative, and the half-life still applies. So we never even needed to know the initial amount to solve this. But still, because the word half-life came up, it means there's a model, a decay model, mass at time t equals initial mass, m at 0, times e to the power k times t. However, this time we can't plug in mass at time 0. We're going to solve for K, and once we do so, we'll be able to solve for the half-life lambda next. Okay, so this is all the information on paper so far. Next thing we can do is work with this equation right here. Mass at time 1, let's take another look at that. When we do mass at time 1, all we're doing is plugging in 1 in for the variable t we see here. So this becomes initial mass, m at 0, e to the power of k times 1. So mass at time 1, I've used this model right here to evaluate it. But we can also do another substitution. We also know from the information given in the problem that mass at time 1 is 0.945, 94.5% of the initial mass. And we can substitute that right here on the left-hand side. Plug in on the left 0.945 times initial mass, m at 0, equals, let me fix that 0 there, initial mass, m at 0 again, times e to the power k. And this is a nice equation because you can just divide mass at time 0 immediately on both sides. In other words, it just completely cancels out. We're free to divide it because it cannot be 0. We're assuming the initial mass is more than just 0, it's some positive number. So divide it out of the equation, and now 0.945 equals e to the power k. I wrote it in with a little bit of extra space on both sides because the next step we've been practicing is just take the natural logarithm of both sides. New cancellation here, and we've solved for k. Natural log of 0.945 is the relative decay rate, k. So that plugs in right there, but the question is half-life instead. So let's say half-life, we write in as a variable lambda, Greek letter. It's defined to be negative natural log 2 divided by k. So that's the formula from above on example 3. From there, we can plug in and say lambda is negative natural log 2 divided by natural log 0.945. That's the exact half-life, but we're going to round it to 2 decimal places, and the units will maintain that information there. It'll be in years. So another step in the calculator, it looks concerning because this looks like a negative number, right? But logarithms are deceptive. If you take natural log 1, you get 0. Natural log of a positive number, like 2, gives you positive quantity. If you do, say, natural log of 0.5, anything between 0 and 1, you get the extra negative sign. So the denominator is a hidden negative sign as well. Altogether, negative natural log 2 divide by natural log 0.945 to 2 decimal places. Let me double check that. Is 12.25 years. So altogether, it's saying if 94.5% of its original amount exists after 1 year, it's decayed to that amount, that implies immediately its half-life is 12.25 years approximately. We'll use this approximate value here for the half-life, or rather, we'll just use the k value here in its exact form to now address part B. How long would it take for it to decay to 20% of its original amount? If it decays to 94.5% after 1 year, we'll use the value k here, plug it back into the model, and solve for that time. Well, the major punchline with part A in this whole exercise, example 4, is just to work with half-life a little bit more. Any last questions at all, folks, before we try out to part B? Okay, before we jump to solving the part B problem, let's go back here and just put in all the information we have about the model. It's mass at time t equals some initial mass. Still, it's an unknown. It's kind of annoying, but it is what it is. We'll work with that. It's e to the power of, I'll put t first, times the relative decay rate, natural log 0.945. So there's the entire model. Now, when we go to this question, we're taking mass at time t. We want it to determine what the value for t should be so that we only have 20% of the original amount. That'd be a decimal, 0.20. When it says original amount, that's the initial mass, m at 0 once again. So solve for t so that we get 20% of the starting amount of this tritium element, isotope. Same approach that we took before. On the far left-hand side, we'll substitute just the entire model. So on the left, it's mass at time 0, e to the power t times the natural log, 0.945, equals 20% as a decimal, 0.20, times mass at time 0. So now that we have that all together, same step as above right here. You can just divide by the initial mass right at this step. It cancels out. Then we'll take the natural log of both sides, solve for t. So let's write that in as a whole new step. Take the natural log of e power t times the natural log of 0.945. It's a lot of natural logarithms all of a sudden, is equal to the natural log of 0.20. Next cancellation, same one since we're example 2 when we saw it. The logarithm cancels with the base exponential, so all that's left is t times natural log 0.945 equals natural log of 20. Then we just divide by that relative growth rate. So t is going to be equal to natural log 0.20 divide by natural log 0.945. So once we have that, our work is done. We'll throw this into the calculator and just round it to 1 decimal place. So this is natural log 0.20. That's a negative quantity, but we're dividing by another negative quantity, natural log 0.945. So to 1 decimal place, it will be 28.5 years. So this stuff disappears pretty rapidly, only 30-ish years to have about 1/5 of the original amount is what this whole process is saying. That's still a while. Well, any questions at all, folks, finishing this one? Okay, this one's a pretty tricky problem that is a good one to refer back to, I'd say, in the homework, because this is just a tricky starting bit of information. It doesn't seem like there's any way we can really work this problem to its conclusion, 28.5 years in part B, based off that minimal information. But really, just knowing that much about a problem, whether it's relative decay rate or a relative growth rate in the problem, you can find a half-life, you can find a doubling time, you can build out the whole entire model just using that information. And you don't even need to know the initial value to work through these problems. Well, that's going to be our conclusion here for exponential growth, exponential decay. When it comes in as an exam question, it'll be for exam 3. There'll be a problem like this, probably either a growth or a decay model randomly selected. And the trickiest thing that ever comes up on an exam problem is watch out for that question, because it's a formula that pops out of nowhere, theorem 2 on the top of the notes. This is the tricky one that we were kind of emphasizing a lot as we went through. That's easy to miss when we do it as an exam question. We'll play around with this kind of model once again for the quiz number 6. We delayed this one because I wasn't as far ahead in the schedule as I thought I was. We took additional time in a chain rule, but that was time well spent, I think. That's a pretty tricky section. Any last questions at all, folks, before we call it a night today? Okay, well, have a great evening, everyone. When we come back on Thursday's class, the emphasis is going to be more about logarithmic functions, whether it's the natural log, log base 10, and otherwise, with a focus on now taking derivatives of that next class of functions. But have a great night, folks. I'll see you all Thursday's class.